working with the different groups on campus. Specifically what I do for Emory is I do a little bit of, I have a really kind of unique position and I really love it, and that's one of the reasons I left private side to go to higher ed, because Emory is basically a small city. So we have all of the same issues, environmental, engineering, everything in between that a small city would have. So I get to do a little bit of civil engineering, I get to do green building, I manage our green building program. I get to work with students, staff, faculty on the sustainability side, and pretty much everything in between. So it's been really, really cool. So just a little bit about Emory for those of you who may not know. We have over 13,000 students, undergrad and grad. And because of our huge healthcare component, we have almost 25,000 faculty and staff. So we're a big place, as you can imagine. Mainly centered right around the Clifton corridor there in Druid Hills neighborhood in Atlanta. Huge operating budget, again, mainly because of healthcare. They're the breadwinners. Our main campus is almost 700 acres, and we have specifically decided to dedicate nearly half of that to preserved land. And as Howard mentioned, that is mostly in our Low Water Preserve, which is a wonderful amenity for the community. And there at the bottom I've shown our 2010 water consumption. So you can see 231 plus million gallons, which is down about 18% since 2007, despite continual facilities growth, population growth. So I think we're doing pretty well in that respect. I encourage you to get onto Emory's sustainability website, and I have the address at the end of the presentation, but it's sustainability.emory.edu, in case you can kind of figure that out. On there, you will find comprehensive description of everything we're doing regarding sustainability. And you will specifically see our numeric goals that we've set for all the different programs, for energy reduction, for waste minimization, all that sort of stuff. However, the one goal we have not put a numeric value to is water reduction. And I'm not really sure why that is, because you can see we have made progress. We're definitely doing things. But I think a lot of it has to do with, at least back when the goals were established, water wasn't such a big issue. Well, fast forward 5 years, and it's certainly a big issue. While we're not as affected as Georgia Tech with the City of Atlanta water rates, especially in the metro area, are going up exponentially every year. So it's definitely something that we want to pay closer attention to. So these are just some of the conservation strategies that we employ. You've heard about so many of them. Green plumbing, as I like to call it, certainly part of our green buildings. At Emory, we have currently 16 LEED certified buildings. And I dare say in a week we might have 17. And we've got 4 more in the works and about 3 in the planning stages. So we definitely have bought into the whole LEED concept and the green building program. That is a program that I manage. I recently got my LEED professional accreditation, and I'm actually acting as the lead consultant on a new freshman residence hall project, just to try to save the university some consulting fees. So it's been a fun challenge as well. But of course, all of the low flow fixtures, dual flush toilets, sink sensors and aerators. With the cisterns, we are in a very similar situation as UGA. We have perhaps 9 cisterns around campus, I believe 9, maybe 10, of traditional underground cisterns that, for various reasons, just are not functioning at optimum ability, let's put it that way. Probably the biggest reason is during our design phase, we tend to have too many cooks in the kitchen with our cisterns. And we'll have a civil design the size and type of cistern, and then he passes it off, and then it maybe sits for a few months, and then the electrical guy will get involved, and then the mechanical guy, and until it's all said and done, we have our commissioning engineer at the end who isn't really sure who's talking to who, and the whole system's not really fitting together. So that's been our biggest operational challenge with our cisterns, but we're trying to right that ship. Of course, all of the landscape management, turf reduction, we have a no net loss in tree canopy policy. We've established a tree bank. For every tree we take down on campus, we are required to either replace or set money aside into a bank for future tree plantings. It doesn't necessarily have to be on the specific project, but elsewhere on campus. Again, with the laser cooling, the closed loop recirculation has saved us a lot of water. And then specifically what I'm going to talk about today are two stormwater and gray water reuse systems that we have recently incorporated into two new residence halls. So, first of all, this is the Few and Evans Residence Hall. It was completed in 2008, 110,000 square feet, 293 beds. It is certified LEED Gold. It is a sustainably themed residence hall, and students actually are required to, during their application process, submit an essay about what sustainability means to them and how they plan to further their commitment to sustainability and how living in a sustainably themed dorm will affect their lives, things like that. The RAs and the other student-led staff in the buildings run themed events surrounding sustainability, so we try to make it a fairly comprehensive culture for the students. The architect on this was Ayers St. Rose. So the stormwater reuse system, I'm going to describe it first, and then if you're anything like me, a picture's worth 1,000 words, so we'll go through some really telling photographs, and hopefully it'll help you understand it a little better. But what the system consists of is a combined bioswale and underground detention structure. So basically it's like a cistern, but it's not a traditional cistern, meaning not a big box, not enclosed pipes. The detention structure was designed to handle, of course, the annual rainfall amount, and it also collects about 300,000 gallons of condensate. And what we use the water for is toilet flush. So the detention capacity is 89,000 gallons. We've calculated a 2,200 gallon demand per day. And that all totals up to an estimated 704,000 gallons of potable water savings per year. However, we are tracking this, and during the building's first 2 years, an average annual additional increase was 27% more than predicted. So we're very, very pleased about that. So this is the system. You can see the new halls there, and maybe a little bit difficult to see. The slope coming down from the top of the stairs, that is the bioswale right in there. The berm is the back of the bioswale, leads out onto a student athletic field. This is the actual system layout. Here's the actual cistern. all right? And so we are collecting water from almost the entire roof system. Everything, this sits on a big hill right here. Everything naturally drains this way anyway, so we're able to route everything, most everything down around the buildings to capture as much as we can. And these are what these storage structures look like. They're called storm tech chambers. And if I go back a couple slides, those sit under the ground here. So they sit about 6 feet down underneath the surface that you see there. It's a big system of chambers that sit in parallel or manifolded together. And that's what the water flows into. So it either percolates through the bioswale, through a specially engineered system of soils and plants that help filter and clean the water, or it directly runs off of the roofs and down through a direct inlet system through these manifolded pipes. Just more pictures of the install. They were set down on, you can see this black liner system. That is a MDPE, medium density polyethylene liner on top of the gravel base, and then the chambers, and then more gravel on top, and then the constructed bioswale above that. You can see they're just covering them up. And that's basically what we have right now. This was taken maybe 6 months after the building was completed. Since then, the vegetation has filled in very nicely. It looks a lot better now. That is an overflow structure that was designed, obviously, if we get any major rainfall events that would inundate the system and cause a backup situation. We don't want that. So we had to build in a system of overflows that would then take the water directly to the storm system. Once everything is in those yellow chambers that you saw, and there is a demand in the building for toilet flush, we have a pump that is powered by these solar panels, and that moves the water from the storage chambers inside the building, where it goes through several filtration systems, and then ultimately is stored in a smaller tank and then pumped up to the bathrooms within the hall. Coincidentally, this to date is one of the very few solar arrays that Emory has on campus. We have not been successful with renewables, unfortunately. Emory is very fiscally conservative, I'll say. So our payback window is very, very small. And while we realize there's certainly an invaluable price to education and public relations and things like that, our administration generally doesn't tend to fund anything with probably less than a 10-year payback. And generally, so far, we've found that most solar arrays do not provide that good of a ROI. So, anyway, this is way difficult to read, I understand. I just wanted to show you, this is a schematic. This came right out of the construction documents. This is the system. Basically, it shows the pipe systems with the lift station there, bringing the water into the building, the filtration systems, the storage, a lot of very technical stuff that is above what we're talking about. We also have the Lucid monitors in these residence halls. I really like the ones that Tech has. They've got the big monster screens that look really cool. We just have these smaller ones. But these are in all of the new residence halls, which right now are 4, soon to be 5. We are building an entire new freshman complex. So these monitors will be in each of those. We've recently got funding to put them in 7 non-residential buildings as well. So we're going to be able to start having competitions among buildings and all kinds of really cool stuff that these monitors do. It sounds like we have the same system at Agnes Scott. So it's a great educational tool. This is the second residence hall, Longstreet Means. This was just completed last summer. 138,000 square feet, 351 beds. We are anticipating LEED Gold on it. It's still in the review process. And the architect, ASG, engineer for this system was Newcomb and Boyd. And this is actually a gray water and a stormwater reuse system combined into one project. So I'll tell you a little bit about that. So, for those of you who may not be familiar with gray water systems, of course you have your black water, which is your purely sanitary sewer discharge. You've got your relatively clean stormwater, and then you have something in between known as gray water. So that's when you wash your hands after you go to the bathroom, that's the shower water, that could be water from washing machines, dishwashers, things like that. In DeKalb County, where Emory is located, they were not familiar with the concept of gray water. So we had to do a lot of education with them, a lot of extra evaluation and presentation, basically, to get them to buy into allowing us to install a gray water system. But it all worked out. I'll go through this real quick with you. As Kevin pointed out at UGA, we also had some operational issues with this, but we've pretty much gotten the bugs worked out of ours, and we feel it's working pretty well now. So would love to compare notes with other guys if that's appropriate. Basically, all the gray water is diverted from those sources. It's taken down into the mechanical space in the basement of the building. It's put through a series of cleansing, and that consists of a lint interceptor, ultraviolet lamp filtration to kill bacteria, some filter banks, and ultimately addition of chlorine. And on this system, the county required us to dye the water. All right, now, can you imagine why we would have to dye toilet water? Sorry? Yeah. Well, I don't know. It's just, as an engineer, it's just counterintuitive to me. But these are students, perhaps. I don't know. Not really against you guys. But you know, I don't know who would stick their head in the toilet to get a drink. But they made us dye the water to differentiate, to physically differentiate that water from what comes out of the water from. So, anyway, that last step is to dye the water before it gets sent upstairs. We calculated roughly 12.5 gallons of gray water per day, 2,800 gallon demand via the toilets, and that's getting us roughly 1 million gallon savings of potable. So this is not chunk change. You know, these are very good systems that for sure were capital intensive, a lot of money up front, but the calculated payback, well, I'm not sure exactly what they are, I'm sure, I know they're very good. And based on the stormwater reuse system in the other hall that I mentioned, we're seeing exceeded savings. So that's only going to make that payback even better. This one I don't have hard performance numbers on yet, but I will in the future. So this is what the system looks like. These are 2 of the holding tanks that the gray water initially flows into to start the filtering process. Right, and then it continues through a series of things that I do not understand, but it's real pretty to look at. And believe it or not, even after a year, this mechanical space is still this clean. So shout out to you facilities guys. So there, tank number 3, that's where the chlorine and dyed water goes. And after everything goes through the filtration, it goes into that tank where it's stored until the demand to be pumped upstairs. And there's the schematic for that one. And that's even more confusing to me than the other one. But it's a pretty cool system. So the stormwater reuse system at this site is a cistern, but as Kevin mentioned, at UGA and at Emory, most of our cisterns are underground, out of sight, out of mind. Like I said, they don't even work right. So it's like, why even talk about it? This one we like to talk about because this is an elevated cistern. Okay, it's a pretty cool concept. It sits over a parking deck and under a green roof. So it's about a 3-foot thick system, and I'll describe it in more detail, that sits between the top of a parking deck and a green space outside of the new residence hall. We calculated roughly 50,000 gallons of water are needed for the site's local irrigation needs. We needed to provide an extra 100,000 gallons of storage capacity as per county code and for detention requirements required by LEED. And then there's also additional approximately 6,400 gallons of condensate per week going into the system during peak periods. For us, we calculated that in the month of July. So you can see, based on our calculations, we do have a 21% reduction in runoff. And because of filtration effects from the green roof, we have better water quality going into the municipal system. So this is the dorm above, obviously. Sorry, dorm. My architect hates when I say dorm. This is the parking deck, and this is the system right there. And what it consists of is roughly from the top going down, about 18 inches of soil and turf on top, and then another 18 inches of, it is the weirdest stuff, that's all I can say. I can't even remember the exact technical, what the product name is, but it looks like, remember old milk crates? It looks like a milk crate, and it looks like a bunch of little milk crates just stacked together, almost like Legos. And when you look at it, it really has like a honeycomb effect almost. And it's just this really hard plastic material that's not even as thick as a milk crate, because you know milk crates are pretty sturdy, you can jump on them and stuff like that. But this stuff has the structural integrity to be able to support 18 inches of soil on top of it. So it's really, it's called a rain tank, that's what it's called, a rain tank system. So it's really just a fascinating product to me. We are having some operational issues with it because it tends to clog pretty easily. The way the system was constructed, we do have filtration blankets and all that sort of stuff built in to help hopefully minimize those effects, but we haven't been able to pinpoint exactly where the stuff's coming in, but we are having some clogging issues. So that's definitely something we're trying to work through. So some of the lessons learned in the implementation of both of these systems. First of all, build in some system logic through your controls and your electronics that allow for maintenance alerts. In both systems, of course, we have to have an override system. For instance, if it hasn't rained, which it hasn't a lot here lately, we don't have rainwater to pump into the system. So there is a logic built in that will sense when the system is dry and will do a manual override to the county's potable system. However, if there's maintenance issues with the system, we don't have a similar override system. So sometimes the system will break down not because there wasn't water, but because of some other maintenance issue, but it would never override to the county system. So then we had no water for any flushing, and you can imagine the complaints we got about that. So that's probably the biggest lesson learned, is that for maintenance situations, build in some sort of system logic to alert staff about those malfunctions. Another big one we had, especially with the gray water system, as you can imagine, assume the water is dirtier than the designers say it is. We worked with a couple different vendors in putting our system together, and of course they anticipate certain types of additional fluids and things like that coming down through the sinks, through the system. But our filters that they said would be able to adequately keep up with those supposed amounts have not been able to at all. The water's been way dirtier than we were told it would be. So we had a lot of operational maintenance issues because of that. These are, as someone else pointed out, very complicated systems. So always make sure to train your operations staff in advance, well in advance, and I think, Kevin, you said, get them involved during the design process. Get their buy-in so they feel ownership of it, and it's not just something that's being handed off to them, and then we and the planning and construction office just go off to the next project. So always try to keep that in mind. This last bullet was really, really big for our stormwater, for any of our stormwater reuse systems. I talk a lot about payback, but that's really, really big at Emory. So it tends to get into a lot of our presentations. But historically, stormwater systems are designed on known data that's been accumulated through the years. Well, guess what? It's not raining like that now. So if you're hanging your hat on getting a certain amount of payback based on getting a certain amount of water into the system, right now is not the time to think that way. So be very conservative with your analysis. Use much lower anticipated rainfall amounts than perhaps required by county code or something like that, at least for your demand side of things. Now, you don't want to go too crazy, because then you'll totally oversize it, and then you're out of balance with your construction costs. But definitely think about that. So just a couple references here, people who contributed to this. Again, here's Emory's sustainability website. It's basically the sustainability Bible of Emory. And that's all I have.